I would define it like based on today's world, and I would define it according to the sources that I've done my research on, and I will define it mathematically as well. So relations are first relations, it comes from the word relationships. A relationship can be something between two people, or a person or a person with an object, and an object with an object, or a person with a choice. I don't know if I'm being too fast, or a person with a choice. I'll take for example, let's say a person with a choice. Let's say I prefer to eat salsa, and the next person prefer to eat pizza. It's based on my my other screen. But before we go further, I'll sorry sir, if you can go back, I'll define it like mathematically, then I can use this. Yeah, thank you. So it can be a choice between a person with another person, an object with another object, or an object with a choice or a description. Sorry? Sorry? Okay. Guys, if you can mute our mics. So let me define it mathematically. Like I said, a relation between two sets is a collection of ordered pairs containing one object from each set. Like if the object X is from the first set and the object Y is from the second set, then the objects are said to be related in ordered pair XY. So that would be a relation. A relation may not be represented by a function, but a relation, it can be a function as well. What I mean is, if it can't be represented by a function, it's because a relation is allowed to have the object X in the first set to be related more than to one object in the second set, unlike functions. So if you can scroll a bit, sir. Thank you. Like I said earlier, a relation can be a choice. Like Peter, he likes salsa, and John likes rice, and Mary likes pizza. So like we said, we have found a relation between the people and their favorite food. So let's scroll to the next screen. Thank you. Next, we will look at the representation of relations. There are 6 methods of representing a relations. The first one being a listing method. The second one is set builder, and the third one is statement representation, and matrix representation, and graph representation. I'm sure you have seen the graph representation in one of our previous assignments, and arrow diagram, we have seen it. The matrix, we have seen it in our assignment, the assignment 1. Then the listing method is the one that is popularly used in our module. So we can scroll, then I'll try to define the listing method. As you can see, like the first one is called listing method, which is R. R is used to represent the relation. So we have one being the X value and the other one being the Y value. What do we mean by the X value? Like we have done in our O-level maths, we know that X value is the first letter on the left, and the Y value is the right letter on the right. So the X value is the input usually, and the Y value is the output. And the X value is associated with the domain of the relation, while the Y value is associated with the range of the relation. Am I clear there? If there's anyone with a question there before we proceed?
Maybe before you proceed there, I want everyone to understand the issue or the relationship between relations and the power set. You have to know that on our previous presentation we talked about the power set in set theory. So here a relation is just a subset of a power set. You need to know that a relation will result from a relationship of a Cartesian product. Like if we say A cross B, those subsets of A cross B will form a relation. I think that's what I wanted to add there. So if you understand the concept of a power set, you need to know that all your relations must be a subset of a power set of the relationship that we'll be talking about. Like for example, that you are giving here, we've got a set A here and a set B. So the relation will be a relationship of A on a set B. What will be the relationship there? So we are saying, let's say we want to represent a relation R, which consists of all ordered pairs X and Y, where X is an element of A and Y is an element of B, and X must be less than or equal to Y, which means we are saying the values in A must be less than or equal to the values in what? In Y. So those ordered pairs that we get will be our relation, which is defined by this condition, which is here, which is X must be less than or equal to what? Equal to Y, which is the X value will be 1, and the Y value here is 1. Why? Because 1 is less than or equal to 1. Then it goes on, 1 is less than or equal to 2, where these values on the Y part are values from the what? From the set B, which will be our range like. And then the values of X will be from what? From set A. I think you can proceed now with your presentation.
Okay, just wanna take this time. Thank you.
Okay.
And to honor our lecturer, I had forgotten about that. Thank you, Mr. Ezekiel Chimana. And also don't forget to like and subscribe on his channel, which is Sachi Online Academy. I'm sure I will share a link immediately after this presentation via WhatsApp. If you can go there, all of us subscribe.
It's fine, I will share.
Okay. Thank you, sir. Let me proceed then. So I've done also my research based on Kenneth H. Rosen 5th edition book. His book called Discrete Mathematics. I don't know how I can say this, but we are not actually doing discrete mathematics, but that's the only sources I could find that that were going along with our topics. So like I said, according to him, a relation is a set of pairs of input and output values. Like Mr. Shimana was explaining, the X value is the input and the Y value is the output. So let's say if you have A and B as element of the relation, we write it as X R Y or A R B, meaning that X is related to Y, which can also be written as RXY as a function. Since relations are functions, it can also be written as RXY. For those who took some logic courses previously, under predicate logic, that topic, never kaita logic, but I'm sure most of us are teenage. But that's how you write it under logic, like RXY. That's how you write it. Then let's proceed. So to the listing method, the first method is quite obvious. It is called the listing method. What you need to do is just to list all the pairs of the relation. As you can see, I've listed down all the pairs of the relation R, that is 1, 1, 1, 2, up to 3, 4. And you can see that the first element is always less than or equal to the second element. It is the so this is the listing method. Now the second method is the state builder. You can see that I can define the relation from A to B, and it must consist of all the ordered pairs of X and Y. such that x is less than or equal to y, or I can say the relation R is nothing but all the set of the ordered pair xy, such that x is an element of A and y belongs to B. That's what I'm saying. Thank you, sir, for pointing that for me. That is the set builder notation. Now, looking at the third method, the statement representation. Upside down or something. But what it means that is for all x belong to A, and for all y belong to B. That's what it actually means. Classical A upside down. For all x belong to A and for all y belong to B. So x is related to y if and only if x is less than or equal to y. This is a statement representation. We are talking about every element of A and every element of B. So now let's look at fourth representation. I really wanted to discuss about this representation, the matrix. This is quite a simple representation, and sometimes it can help us to find the solution of the question easily. I'm sure we are familiar with the word cardinality. Are we familiar? Anyone asking us what cardinality actually is the number of elements in a set. So let us suppose the cardinality of A is M and the cardinality of B is N, according to my picture that I've sent there. So it means that we have M elements in set A, M for mother, M elements in set A, and N elements in set B. Then obviously we can create a matrix size of M times N. There will be M mother rows and N, hello? And N columns, and it rows and columns. For example, we have 3 elements in set A, which means there must be 3 rows in the matrix. So the rows are the ones coming from the left to the right. I'm sure. Can you say, if you can please change the color for the rows for our viewers?
Just wait. There's someone whom I need to mute, but I'm not seeing here. Okay. Guys. It's hello, Eva. Can we mute ourselves?
It's Perfius. The account is called Perfius.
Yeah, it's okay.
So if you can highlight the color for the rows for me.
For the rows.
Yeah, I think they were on top.
Okay, just wait. Let me try to use the different colors. This one.
Okay.
I think.
Yes, sir.
For rows here.
Yes, sir.
Don't know how are we going to do it. It's okay. Let me.
So as you can see, from the rows are done from the left going to the right. Right, and we have 4 elements in set B, meaning we will have 4 columns in the matrix. Anotsika pass ndoma columns, guys. Tichitsika pass ndoma columns. Tichenda ku right ndoma rows. I'm sure we've passed through that, but it's our O level. But O level yedu. So kana pana asingaziye cause zvichadzoka again kana takuzoita na HTML takuta Gemma rows and columns. I'm sure you see it, so please take note. I really wanted to discuss about this topic here, my matrix. So now let's look at the 5th representation. Now just highlighting my representation, my relations. The 5th representation is it's called a directed graph, monolithic graph representation. And I'm sure we have seen it in one of our assignments. So what it means is a directed graph, you can see there are elements of set A and elements of set B. By those knobs, the round circles, the elements of set A and elements of set B. And on top, I've written all the elements of set A, and on the bottom, I've written all the elements of set B. On top, I've written all the elements of set A, like 1, 2, 3. Then on set B, I've written 0, 1, 2, 3, 4. We are using the same set on the same page on top, whereby B is equals to 0, 1, 2, and 4, and A is equals to 1, 2, and 3. So you can see I've drawn a line from 1 to 1 with an arrow. That one being highlighted by say that's 1 to 1 from top of the knob. As it is also part of our relation where there is an arrow under number 1 where it's written listing method, we are given 1, 1, meaning it's 1 and 1. And we are given 1 and 2. So there must be an arrow also coming from 1 and 2. Then we are given 1 and 4. As per our assignment, like we have seen in our previous assignment, and it's really a walkover there, guys. I don't think pane chinonetsa. But if something is representing itself, like if it's reflexive, there will be a circle on it. That's what that is all I can say about the directed graph for now. But let's consider another way of representing a relation. Is called the arrow diagram. It's on the next page. The arrow diagram. The arrow diagram. I'm sure we have seen it in most of the questions in our assignments. We have seen the arrow diagram. Also, you will see it as we are doing some functions. So I wrote all the elements of set A and on the left, and all the elements of set B on the right. The lines between represent the mapping of the relation. We have lines drawn from 1 to 1, 2 to 2, and 3 to 4. 1 to 2 is based on the elements on our sets. So basically, kids, basically there are 6 ways that you know that you can use to represent a relation, and maybe there might be others that are out there that I don't know yet, but based on my module and the level of my understanding, I know only these 6. So I may not argue, or I may argue, but these are the 6 that I know, that I've been taught. So if there's someone to blame about that, you must blame the lecturer.
And for this module are enough.
Yes, and yes.
Yeah.
So
Also, also on the issue of a directed graph, there is a terminology where you can be asked to give a diagram. It's a directed graph. You have to know that. Yeah. If you are being asked of a diagram, you have to know that it's a directed graph that you are being asked for.
Okay, sir.
Yeah.
Thank you for that enlightenment. So if you can skip to the next page. So now I want to look a little bit deep on the types of relations on a set. Types of relations on a set. Yes, there are quite a few, and I'll try to start with reflexive and symmetric relation, anti-symmetric and transitive, but the main ones are reflexive, symmetric, and transitive. If you can master those, then you can master the rest. I will start with reflexive. As it suggests, the measure of every element of a set is its own reflection. Reflexive relation is an important concept in the set theory. For example, the relation is a subset of a group of sets. Its reflexive relation is is a very set as every set is a subset of itself. What it means is the reflexive, when something is called is being reflexive, it means it's representing itself, like basically x to x, not x to y. I don't know Canada neighbor web up, but it's x to x, it's representing itself. It's reflexive. Me myself, I tend to think of it like a mirror. That's how I remember reflexive, like a mirror, because it's reflecting itself. So there are different types of relations that we study in discrete mathematics, such as reflexive, transitive, and symmetric. In this presentation, we understand the concept of reflexive relations and the formula to determine the number of such relations, along with some solved examples for the better of our understanding and for the better of this module. So I'm sorry if I will like overlap into something that is not based on our module, but I'll try to stick on to that. And we have our lecturer there to guide me. Some of those things won't be for our level.
It's fine.
Okay, sir. Thank you. So in set theory, a binary relation, right? Binary relation on set A is said to be reflexive relation if every element of the set is related to itself. So let us consider this mathematical example, right? To understand the meaning of this concept, let's define a relation of the set of integers. Integers are represented with a capital letter Z. Right. Now we know that the integer is equal to itself, such that 0 is equal to 0 and -1 is equals to -1 and 2 is equal to 2, so on. So this implies every integer is related to itself. Hence, the relation is equal to or on the set of integers is reflexive relation. Like I've said there are multiple ways to represent the relation. So let's say we want to represent the relation R, which consists of the ordered pairs XY, where X is an element of A and Y is an element of B. X is less than or equal to Y. I don't know, say if there's someone who has got a question, or you may need to add or remove from there before we proceed to symmetric.
I think it's all fine. Maybe you have to explain, maybe, or give a clarity on this example, just demonstrating.
Yeah, the examples I have them like based on my presentation at the back. I have quite a lot of examples at the end
Do
of
we have
this presentation.
no. I was thinking maybe you have something like which is a practical, where we'll be showing that when you are saying a relation is reflexive, this element,
Yes.
like if it is we are saying x must be less than or equal to y, which means for every value in A, we know that it is either it is less or equal to itself. So in our relation, there will be a value in set A which will be mapped to itself. Each and every element in A will be mapped to itself. That's a reflexive relation. So for others, it will be easy for others to understand if you give something that they can see, you know, on your presentation. Maybe we're supposed to demonstrate like the ordered pairs, the actual ordered pairs here. They were supposed to be listed.
Okay, I understand. So,
Yeah.
like a good example for that. Let's say we have one. Let's say one can be less than or equal to 2. Is 1 less than or equal to 2? I didn't wanna. Sorry to argue, sir. I'm sorry to argue.
Yes. Okay.
I didn't want to overlap with this kind of topic because it will take me to truth tables as well.
No, just using the basic examples. Let me see if I have one here. just using basic examples so that others can see. I don't know if they understood. If they understood, you can move on. But maybe let me see if I have got an example for reflexive relation.
Okay, sir.
Yeah, something like this. Let me change the slide that I'm sharing. Let me share something.
Okay, sir.
Something like this. Like here, if we consider the following relations on a set, maybe set A, which is 1, 2, 3, 4. We have got a relation R1, a relation R2, relation R3, relation R4, relation R5, and relation R6, where you are supposed to show which are reflexive relations. You see, so because these ones are the question that you might be asked in an exam. So I need people to see and to know how to do it. That's what I was saying. Like here, let's consider relation R1. We've got 1, 1 here, which is good for our reflexive relation.
Reflexive, yes.
Yeah, but do we have 2, 2? Yes, we have 2, 2. But do we have 3, 3? No, we do not have 3, 3. Then we can confirm that R1 is not a reflexive relation, since we do not have 3, 3 in our relation, or when 3 is mapped to itself. Also, we go on to R2. R2 definitely it's not a reflexive relation. Why? Because we do not have a 2, 2, we do not have a 3, 3, and we do not have a 4, 4. Just something like that. Someone mute? Don't know who have got a phone who forgot to mute yourself also. Can we make sure that we fine? It's okay. So on R3 here, we've got 1, 1, we've got 2, 2, we've got 3, 3, and we've got a 4, 4. Then R3 is what? Is a reflexive relation. Why? Because we've got all the members of this set mapped to itself or to themselves. Then we move on to R4. R4, is it a reflexive relation? We check, do we have a 1, 1, a 2, 2, a 3, 3, and a 4, 4? We do not have them. So R4 is not a what? Is not a reflexive relation. Then we move on to R5. There we have got a 1, 1, we've got a 2, 2, we've got a 3, 3, and we've got a 4, 4. Therefore, R5 is a what? Is a reflexive relation. Then for R6, it's not a reflexive relation. Why? Because you do not have a what? 1 being mapped to itself, 2 mapped to itself, 3 mapped to itself, and 4 mapped to itself. So that's what I was asking you for to provide. Yeah. Maybe you can move on to symmetric relations.
Why was still there, sir? But can I ask?
Yes, you can ask.
I came across something like, let's say I'm testing my reflection, my reflexivity with I don't know the word exactly. Let's say I'm testing it, right? And all the properties they match like reflexive.
Yes.
But yet the sign doesn't hold.
Like the sign, which sign?
Let's say there will be, let's say I'm not dealing with reflexive, let's say I'm dealing with transitive. Yes. Like the sign doesn't hold, doesn't make the logic true.
No, I think what you have to assert here is to confirm, like what we have here. You are asking for what? For a sign, right? So the sign,
like if the numbers match, say if the numbers match transitive and the logic doesn't match the transitive, what do we do from there?
I think it have logic operator, because the logic, you need to consider the logic first, and then you consider the transitive relation.
Okay.
So because the logic will give you the ordered pairs first, and then you test if that are set to the relation type. I don't know if you get me correct. Like here, like here we've got relation R1, and we've got all these ordered pairs, but we do not know the logic that was being used to select these subsets. So what we are what we are seeing here is just a list of subsets that were taken from this set, and then we want to confirm if it is a reflexive relation. So what we test is that for all elements in A, are they mapped to themselves? If they are mapped to themselves, we can confirm that R1 is a reflexive relation. But the logic will be the one that we use to select the ordered pairs.
There is a logical operator set that tends to be confusing, like the not equal sign.
The not equal sign.
Let's say I'm trying my you gave me a question, say like 4 minus 3 is not equal to 0. Then you said determine if it's reflexive, symmetric, or transitive. 4 minus 3 is not equal to 0.
Yeah, I think you need to give some counter example first there, and then you need to assert for reflexive, for transitive, or something. Maybe it might be need us to write the sets or the subsets so that we can actually confirm if it is a reflexive or something like that.
For it can be as reflexive, but it can be symmetric. To some point, it can be symmetric, because according to the truth tables, there is a point whereby if something is false, everything is true. And it makes that statement true somehow. Then also under transitive, it makes it true as well. So I don't know how we go about those kind of questions, but it would have been nice, say, if you can organize another day to look at those kind of questions, and we don't know what's coming in the exam.
Yeah, for sure we do not know what will come.
That's weird, don't worry.
I don't know. At it as weird, don't worry. We'll give you something to read. And if you stick along those lines, you will never go wrong. There are some part of examples in your module and in your slides that I've put on your portal. So you need to read along those lines. If you go something that goes beyond that, if you see something that goes beyond that, you can do it on your time. But mostly likely it's not going to be in your exam.
But fear drives us, mates tend to be afraid.
So I think we can proceed with our presentation, but it's also good to read why. It's also good to read wide. So let me share so that you can do the symmetric. But I don't know if there is any question from the floor. I'm not seeing any hand or so I assume that everything is going well. So let me share the slide that we were using. I think we were here.
Symmetric.
Yeah. So
sorry, sir. Sorry, sir.
Okay.
Sir.
Yes, go ahead.
Sir, that's your PowerPoint.
Hello.
That's your PowerPoint.
It's there on your portal. It's there on my Vista. You can download it.
No, okay, but let's go up here and look what happened.
Maybe. Hey, I will try to share all of them on our WhatsApp group.
Okay, thank you, sir.
It's okay. I think you can.
Guys,
you can proceed.
We can proceed now.
Yeah.
Thank you, sir. So we're like on symmetric. Unfortunately, I had not brought some picture examples. I'm really sorry for that, guys. But I'll try to explain as much as I can. So what do you mean by symmetric relations? Symmetric relations, like I said, I've done my research in a book for discrete mathematics, and it's one of the modules. It's optional. That will be coming, I think, in the part 3, part 2, part 3. It's optional if you want to continue with discrete mathematics, but I wouldn't. I'm at Antifara, so I wouldn't choose discrete mathematics. So like I said, symmetric relation in discrete mathematics is between two or more elements of a set.
To our presenter, just waiting for him to log on again. I don't know what had happened to our presenter. So I think I can proceed from there while we are waiting for him to come back online. So on symmetric relation team, what we'll be looking at is a relation on set X where X, Y is an element of X. If X, Y is an element of what? Of our relation, then YX is also the element of our relation. What does it mean? Whenever we have got X mapped to Y, we must also have Y mapped to X. It's like an R which is going forward and also an R which is going back on those two elements. So they might be the same where X is equal to Y, or where X is not equal to what? Not equal to Y. I'm trying to add other people here. So that's a symmetric relation. So here there's an example. Just wait, I'm communicating with the presenter.
Hello, sir.
Yeah, hello. Sorry, I was actually carrying on. So I was on.
Sorry.
It's okay. Which one?
My other device was put out, so I'm just trying to reconnect again.
It's okay. I saw you. Let me make you an attendee. Just wait a little bit. It's like.
I'm back now.
What's your username now?
I'm using the same number now. I'm back with the old device.
Username, like name that you've used while logging in. What I saw you.
Talent machine.
Talent. It's okay. I saw you. It's okay. So you can proceed. I was about to do an example on symmetric relation. You can proceed.
Okay. You can go ahead and say. I don't mind.
Not you don't mind. You have to do. You have to. You have to mind because it's your own presentation.
Yes. Okay.
It's okay.
I prefer your wisdom.
I know you can proceed.
Okay.
Yeah.
So like I said, symmetric relation in discrete mathematics is between two or more elements of a set, such that if the first element is related to the second element, then the second element is also related to the first element as defined by the relation. So what I mean is that if X is related to Y, then Y is related to X. That's all it really means there by symmetric. There's a word like symmetric relation is binary. It's a binary relation. Okay, I'll look at that a little bit later. So symmetric relation by definition, it's a binary relation. R is defined on the set A for elements A, B, A and B being an element of set A. We have A R B, that is A, B being elements of R. Then we must have B and R, B R A, that is B A being elements of R. So I had no written examples that I could share the picture.
I think we have one here.
Mr. Richard.
This one, or let me find.
I just wanted to point out that I can't see the presentation. I'm not sure whether it's myself only or with the other guys.
It's okay. Sorry. Let me share. Do you have something now?
Sure.
Yes, sir. Yes, sir.
Yes.
It's okay. So let me try to find an example for symmetric relation, so that we can do a quick example there. Let me see. Let me share something. Yeah, I think we have got this example
On R2.
This is an example which says let A be a set which is equal to 1, 2, 3, 4, and define relations R1, R2, R3, and R4 on A as follows. Where R1 have got these subsets. R2 is equal to this, and R3 is equal to this, and R4 is equal to this. So we are required to show if, or to confirm if R1 to R4 are symmetric relations. So what are we supposed to do here? Let me find a highlighter here. I think this one will work. So what we are supposed to do here, on R1, we know that 1 is mapped to 1, and also 1 is also mapped to 1, because only our symmetric, we say whenever we have got x mapped to y, you must also have what? Y mapped to x. I don't know, there's a background noise. Don't know. Yeah, it's this one. Okay. So whenever we've got x, y, you must also have what? Y, x. So for this one, we've got 1, 3. We need to confirm if we have got 1 and 3 here. We need to confirm if we have got a 3, 1 in this relation, and we have 3, 1. We've got
1.
2. Yes, we've got 2, 4 here. Do we also have a 4, 2 in our relation? Yes, we've got a 4, 2 here.
Yes.
So we can confirm that R1 is a what? Is a symmetric relation. That will be the logic that we'll be using. So for R2, we've got a 1, 1 here, which means whenever we've got an element mapped to itself, or whenever we have got a loop, that loop will be enough to assert that the relation or that set will qualify for a symmetric relation. So we have got a 1, 1 here, and we've got a 2 mapped to itself, and we've got a 3 mapped to itself, we've got a 4 mapped to itself. So we can say that R2 is also a symmetric relation. Why? Because x is mapped to y, also y is mapped to x. We are doing it just only a same set, which is different from say 1, 3, and 3, 1. It's like 1, 1, and 1, 1 on the same set. So on R3 here, relation R3, we've got a 2, 2. We've got a 2, 3, but we do not have a 3, 2. We've got a 3, 4, but we do not have a 4, 3. So R3 is not what? Is not a symmetric relation. And we've got R4. We've got a 1, 1, a 2, 2, a 3, 3, and a 4, 3, but we do not have a 3, 4. So R4 is not what? It's not a symmetric relation. So I think that's all on a symmetric relation. I think you can move on to the next type of relation. Let's try to move faster. Okay, so let me try to share the actual. Any question? See. You can unmute yourself. There's a hand by Robes and it's so Tsitsuke, do you have any question?
Yes, sir.
Yeah, you can ask.
It now seems as if symmetric and reflective seems to be the same. What's the difference now?
Yeah, a relation can be a reflexive, also it can be a symmetric relation.
Okay.
Yeah, what you need is to confirm if it holds for. You need to confirm if it holds for what? For a reflexive relation. Also, you need to confirm if it holds for symmetric relation. Once it holds for that, then you need to consider what are you asked for. I don't know if you get me correct.
Yeah, I get it.
It's okay. So you can mute yourself so that others can ask. Don't know if there is any more questions. So I think we can move on to the next example.
Okay.
The next
guys,
type.
before we proceed, guys, sorry, can we mute our mics? Zanele. Thank you. Zanele. So what the lecturer is trying to say by you must try it if it holds? It means you must apply the formulas for each and every question. You must try it for anti-symmetric if it was. What we are doing, guys, is we are doing software engineering and IT. Basically, what it means is we'll be designing softwares and we'll be designing softwares here and there. So if you design something that doesn't go along and it becomes, you say the software's got a bug or something, because it's not holding. What you are telling the math behind the software won't be logical. So what it means by saying by what he's saying, like you must try it to see if it holds. How do you try that? That's what it means. So whenever you are given a question, I'm just being cautionary there. Whenever you are given a question, don't rush to say this is reflexive, this is transitive, and try it for everything. Try it for everything before you get your answer and see the possible outcome, the one that suits best, the one that is perfect.
Also check the question. Also check the question. What are you asked for? If you are being asked to prove if it is a symmetric relation, then work along symmetric relation. Do not try to bring other relations.
Yeah, like if we look at sorry for this. If you look at number 1 from our assignment 2, we are tasked to check if it is equivalent. So
yeah,
when it is equivalent, it means we have to try it for everything. Is it reflexive? Yes, it holds as reflexive. Is it symmetric? Yes, it holds as symmetric. Is it transitive? Yes, it holds as symmetric. So then it's transitive, then it means it's equivalent. So you need to try for everything. Don't just take my shortcuts when it comes to these tricky questions, guys. That's my advice.
Yeah, also on this issue, I'm seeing the neglect the issue of equivalence relation. On your slides, there is no an issue on equivalence relations. I think it's something that you were supposed to put in your slides, because when you are talking of equivalence relations, you need to know that which are relation types that will be considered. Because only an equivalence relation, there is no anti-symmetric, there is only reflexive, symmetric, and transitive relation.
Yes, sir.
Yeah, so I think it's a point that you have missed there. Maybe it's one, you are the one who brought it.
Yeah, questions for all.
Yeah, it's okay. So
okay,
I think you can proceed.
All right. So next I will look at anti-symmetric. Anti-symmetric, that's the one we're looking at. In discrete math, a relation is said to be anti-symmetric relation for binary relation R on a set A. If there's no pair of distinct or dissimilar elements of A, each of which is related by R to the other. In a formal way, what I'm trying to say is relation R is anti-symmetric, specifically if for all A and for all B, in A if R, right, let's say bracket xy, right, with x is not equal to y, then the relation between y and x must not hold as well. Or equivalently, if r and x, r of x and y, right, and r of y and x, then x is equal to y. Whenever x and y is in a relation R, then y and x is not true. So here x and y are the elements of set A, but for the second part, it should be not true. Like an example of antisymmetric is for relation is divisible by with the relation for ordered pairs in the set of integers. For relation R, an ordered pair xy can be found where x and y are whole numbers and is divisible by y. It is not necessary that if a relation is antisymmetric, then it holds Rxx. Like Titi has asked, if something is antisymmetric, then it becomes reflexive. For any value of x, which is the property of reflexive relation. Not if a relation is not symmetric, that does not mean it's antisymmetric. I hope man this is a pub. If it's not symmetric, it doesn't mean it's antisymmetric. And sometimes we are given, like our lecturer does, I've noticed that sometimes he gives us questions, animal values and x and y. Can you try to change them into integers and test them if they will hold before you conclude your answer? Because you can't say if something is transitive, yes, x is greater than or less than y, yet y is greater than or equal to z, but x is not greater than or equal to z. You can say that, but what if they are figures? What if they are digits? Is your answer going to hold? So you need to be careful there, guys, about antisymmetric. I don't know, say if you have some good examples, but I think I'm ready to proceed. Antisymmetric.
Yeah, I think I can have one. Let me check.
Okay.
Yeah, let me change the slide that I'm sharing. Oh, I was not sharing anything with you.
Yes.
Sorry for that. You were supposed to remind me.
Is holding. Titi, you can go ahead while says looking. I see you holding your hand up. Titi? I think she just left the.
All right. And Mona Lisa there. There's Mona Lisa. Yeah, Mona Lisa is
can go ahead.
Ndakandisingaone saka ndachida kuconfirm kuti ndini here kana kuti because panguva uchiexplaina ndandisingaone anything.
It's okay.
Okay.
Yeah, ndakanganwa kuita reshare slide ratari kushandisa. Anyway, let's do an example on an antisymmetric relation. I'm sure I'm sharing with you the slide. Yeah. So here we've got a set A, which is equal to 1, 2, 3, 4, which have got the following relations, which defines the following relations, R1 to R4, which is the R1, R2, R3, and R4. Then we need to assert if all these, if a given relation is what is antisymmetric. Like here, we have got R1. R1, you've got the subset is 1, 1, and 2, 2, and 3, 3. We can confirm that R1 is antisymmetric. Why? Because whenever we have got x, y in an element of what? Of R1, we do know, we also have 1, 1 again is what? Or x, y is what? Is an element of R1. That's why we say this one is what? Is an antisymmetric. The thing is that whenever you have got like a 2, 3 here, you must not see a 3, 2 for it to be an antisymmetric. For R2, is anti-symmetric, but is not symmetric. Why? Let's check. We've got a 1, 2 here. And we've got a 2, 2. We've got a 2, 3. We've got a 3, 4. And we've got a 4, 1. For these, we see that for every different value of x, y, there is no another element, or there's no another subset which is doing the opposite way. Like you've got 1, 2, we do not have any 2, 1 here. We've got a 2, 3, we do not have a 3, 2 here. We've got a 3, 4, we do not have a 4, 3 here. And we've got a 4, 1, we do not have a 1, 4 here. So by that, and we've got a 2, 2, which is also equal to 2, 2 again, whenever if it is the value of y or the value of x, because x will be equal to y. So this one, it's a what? It's an anti-symmetric, but it not also holds for what? For the symmetric relation. Let's go on R3. Let's see if R3 is anti-symmetric. Here we've got 1, 3, and we've got a 3, 1. So we've got 1, 3, and a 3, 1. Whenever we have got a value of x and y which is not equal, we must not have the value of x, the value of y mapped to the value of x again in that relation for it to be anti-symmetric. So R3 is not anti-symmetric. Why? Because we've got a 1, 3 and a 3, 1 here. But if we look at it, it is also a symmetric what? A relation. Why? Because we have got a 1, 3 and a 3, 1. We've got a 2, 4 and a 4, 2 and a 2, 2. So it is symmetric, but also it is not what? Anti-symmetric. Then here R4, let's check if R4 is a symmetric relation. We've got a 1, 3 here and a 3, 1. Then it is not an anti-symmetric relation. We've got a 2, 4 and a 4, 3. So here it is also not a symmetric relation. Why? Because we've got this 2, 4, but we do not have a 4, 2 for it to be a symmetric. So this is the example for a set if a relation is what? Is anti-symmetric. But also to take note of that point, if a relation is not anti-symmetric, it doesn't mean that it is a symmetric. And it is confirmed by this relation R1. Because R1 is both anti-symmetric as well as symmetric relation. So whenever it is anti-symmetric, it doesn't mean that it is a symmetric relation. So I think you can move on to the next slide if there is no any question there. I don't know if there is any question. Any questions? So I think I can share the slide for our presentation, and then you can move on to the next on a transitive relation. It is transitive relation here. Okay. Here there is an omission.
I would have preferred transitive.
Yeah.
Is there an error, sir?
It's a transitive relation.
It requires 3.
So you can carry on with the presentation.
Okay.
Yeah.
So okay. Oh, I noticed it. So transitive relation are binary relations in a set theory. They are defined on a set A such that if A is related to B and B is related to C, then element A must be related to element C. What I'm saying is for A, B, and C in set A. To understand this, like I said, I really advise guys to change my words into my integers. But for now, for today, I'll just I'll give an example of using my alphabetical letters. So let's say a relation R on the set of integers, a relation R on the set of integers, a relation R on the set Z, Z meaning integers. A is related to B if and only A is greater than B. Now assume that A, B, and C in integers in Z, right? A are B and B are C. Therefore, A will be greater than B and B will be greater than C. We know that for integers, whenever A is greater than B and B is greater than C, we have A greater than C, which implies it's related to C, that is A is related to C, hence R is transitive relation. I don't know, Panas now to say papere. Ditangit. Panas now to say pap. That let's assume for integers A, B, and C.
There's Sylvester. There's Sylvester. I think
Okay,
you got a question.
Okay, you can go ahead, sir.
Mina ndanyatsopanzwisisa patransitive apa kwati inenge ichiti chingondidzokoredzerawo bijana ndokumbirawo.
Zvine mari mukati rese.
Let me find if I've got an example. Maybe an example will help.
Okay, while he's looking for example, let me try. Transitive usually requires 3 or more.
Okay.
While we are still looking, sir, transitive usually requires 3 or more elements, A, B, and C, and it comma Sylvester.
Yes.
And at A is greater than B and it, then B is greater than C. Chichira is A is greater than what? Than C.
Okay.
What a B in comma Sylvester. Comma with the same. So like I advised earlier, and attack with my relations. Let's try to convert the letters into numbers, into digits. That way it will be easier for us to my answers are hold and it.
So here, Tim, I think on transitive relation, you need to understand it's different from other relations in the way that, in the sense that it considers 3. You'll be having 3 elements, which is three, which is X, Y, Z. So if X is related to Y and Y related to Z, it means that X is also related to Z. That's what about transitive relation. If X is related to Y and Y is also related to Z, it means that X also have got a connection here with what? With the Z. X will be also related to what? To Z here. So for an example here, we've got this example, which is a relation on set what? On set X, which have got A, B, C, D, which is given as follows. We've got AB, AD, AC, BC, BD, and CD. We need to assert if it is a transitive relation. So here we've got AB. Whenever we encounter a B something, we need to know that A must be also related to that thing or to that element. So if we've got AB, we have got a B something. Yes, we've got BC, which means also an A must be also related to C. So we have got AB and we've got BC. So A must be also related to what? To C, which is AC here. So we have got AD. Whenever we have got a D something, A must be also related to that something that we get. So do we have a D something that we do not have it? We've got a BD, but do we have any relation that starts with a C? We've got a BC here and a BD and then a CD here. We've got this and this. So we can confirm that this relation is what? Is a transitive relation. I don't know if there is any question here or if you get it.
Commercial first. What our teacher is trying to say is imimi mune mhuri yenyu mukoma, imimi mudzimai wenyu nemwana wenyu. Mwana wenyu anoenda kuchikoro odzoka aine covid, osadza mudzimai wenyu covid, amai vake, then imi mosarawo covid. Auya necovid ndiani? Mukafunga kuti maiwana covid, hanti yakabva nemwana.
Yes.
Mandisisa.
Aiwa.
So meaning right, kana kuti amino enda pa kuti example.
Inadipo hapo Adolf ane question.
Ndibate zviri zvimwe zvirwere mukoma. Ndane chirwere mumbandi yako.
Let's go to Adolf Chidongo. Do you have any question?
Go ahead, say you can ask.
Yeah. Nada kubvunza pane uye utanga.
Ipi.
Pane question yekutanga. Tatanga transitive relation. But example yacho manje yabva. Ndopana chida explanation pekutanga.
All right, it's okay. Let me reshare that slide. Maybe. On what? Is it here?
Yeah, apa explanation yacho tanga ndonyazonzwisisa.
Okay. So here a relation, it is transitive relation for all A, B, C is an element of A. If A, B is an element of R and B, C an element of R, then A, C is an element of R. What you are saying, whenever you encounter in your relation A related to B and B related to C, in that same relation, you must have A related to C. If you do not have that, it means that that relation is not what? Is not a transitive relation. I don't know if you get it.
Right, in the bracket
Comma out of.
Pane noise ukiitika pa mic.
Come out of nyaya iri papa iri simple. Let me try to explain and it. Zvikureva kuti imi mukoma out of lesson A munoshanda nemurume anonzi B muoffice imwe chete, but B anoshanda nemurume anonzi C muoffice imwe chete. Imi mamushande na C here muoffice imwe chete kana muchishanda na B anoshanda na C muoffice imwe chete.
Alright, tina pana A na B apa.
A indimi handiti mukoma out of. Inini ndini B. Tinoshanda tese muoffice imwe chete handiti. Then inini ndoudza vanhu kuti ndinoshanda na C ava muoffice imwe chete. Azvireve kuti mimere hamushandewo na C musame office.
Okay, yeah, through B.
Handiti.
Yeah.
Mapanzwisisa mukoma.
Okay, andapabata.
Saka da kukupai ma questions.
Mona Lisa, is that a hint? Mona Lisa, is that a hint?
No, I mistakenly clicked that.
It's okay.
So this is transitive. Okay.
So I think
this is transitive. And ndichine tumwe twandangowedzera wangu tusiri pa
slide.
Unless mudaenda lunch say.
Not ndoda kuenda lunch. Maybe I can give you 9 minutes, but you need to include them on your slide. Then you send that slide to me so that others can go through it.
Okay. Like I said, it was a question I had raised earlier to check if the operator is reflexive, symmetric, or transitive. So it's an equal, it's a less than or equal to sign. I'm sure I tested to know as less than or equal to sign. So how do you test it? Transitive, reflexive, or symmetric. So let's say one is less than or equal to itself, and it.
Yeah.
So this means it can pass from a reflexive since one is less than or equal to what? To itself. It can test for reflexivity, pass it to hold. And it.
Yeah.
What about what if I'm given a different number like 3 and 4? Is 3 less than or equal to 4?
Yes.
Is it less than or equal to 4? Is it equal to 4?
You know what? I think it's the basic logic there. When you are, I think you have misunderstood the less than or equal to operate. Because if I'm saying, what you have to understand is that if I'm saying x is less than or equal to y, it's in or operator. X is less than or equal to, which means it is either less than or equal. So it is true whenever it is less than or equal. So you are considering the less than and the equal part. So 3 is less than 4. Yes, whether it is equal or not, once it is less than, we can consider it. Also, is it 1 less than 1? No, it is not less than 1. Is not less than 1, but 1 is what is equal to 1. So we also take 1 is less than or equal to 1, since we are using an or operator between less than and equal.
So say you are saying if 1 is true, then everything else is true.
Not everything else. What are you considering? You need to give a counter example.
Like I'm just asking. I'm not arguing actually.
Yeah, you are not arguing, but I think I'm stating the facts as they are. Because if 1 is less than or equal to 1, does it mean 4 is less than or equal to 3? No, 4 is not less than or equal to 3. So we cannot say it is true for everything. That's why I'm saying you need to give a counter example.
Like I said, I had some questions. For this, say I was going to look down at 3 being less than or equal to 4, right?
Yeah.
Is this equality not symmetric, sir?
Yeah, I think that's where you have to give a counter example or something in writing where you can substitute some variables and then you can confirm if it is symmetric or not. For something which is symmetric, what are the conditions that we need for it to be symmetric or not? What are the elements of that set? If you list all those things, it will be easier for you to determine if it is symmetric or anti-symmetric. Not the shortcut way that you might be wanting to say if this one, if I give you this operator, is it a symmetric or not? I need the reason. Why are you saying it is symmetric? Why are you saying it is not symmetric? Where are the counter example? Which means you need to formulate if it is a set, because it's already in a set. If I say whenever x is less than or equal to y, which means you need to give me an example when x is less than what is less than y. When you give those examples, now you need to confirm on that subset or on that relation that you have put if it is what, if it is symmetric or not.
Okay, I understand, sir.
Yeah, that's the logic there. I think
I don't know if it's part of our module to do arbitrary values. Do we?
Not per se, but since it is also under relation, I might ask it, because it's just the same. We are doing it's something like which is almost like it is advanced, but it's not advanced. We are just using the same basics.
Okay.
So even if you check in your assignment, whenever I asked you to prove if it is a symmetric or a transitive relation, I asked for a reason.
Yes, sir.
Yeah, so that's what it is. So if you know, if you can,
if I have a reason.
Unogona kunyeba zvako haurambidzwe, but kana kunyeba kwako kusingatipi zvakanaka hauwani maki, ndo pane problem. Yeah.
I understand. So thank you, sir, for the time. I'll leave everything to you, and thank you guys for being part of the meeting. I don't know if there's anyone else anything so Quantity or say, but I did try my best based on my understanding, and this yo kana pane zvandasirira kana kuda kuwedzera anyone angado.
I think pane issues equivalence relation.
Okay.
That one, yeah, of a equivalence relation. And I'm sure there was the other part that I was thinking, the partial order. There's a partial order relation. Whenever you are asked to confirm or to assert if a relation or if a set of relations or if a relation is a partial order, you need to show that if it is a reflexive, anti-symmetric, and a transitive. If you're asked to prove if it is an equivalence relation, you have to prove that it is a reflexive, symmetric, and transitive. So the difference between the partial order and the equivalence relation is on anti-symmetric and symmetric. So you need to check on those two on those two things. I think
okay, sir.
That's all that I can say there.
Thank you, sir. I really appreciate
Okay, so have a good day. I'm out for this meeting.
Thank you, sir. Thank you, guys.
Yeah. I think for the next presenters, you need to up your gear, and you need to also to submit your presentations earlier, your slides earlier, so that I can go through. Maybe you'll be having some parts that you need to edit or so that I can tell you in time. So guys, thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.